everyone, welcome to VT chat. So we have already discussed about adders and subtractors, right? Now I am going to explain about magnitude comparator. So generally what is comparator? Comparing any two numbers, right? So we will compare any two numbers which has certain bits like 2-bit numbers, 3-bit numbers, 4-bit numbers. We compare these two and we'll draw the combinational circuit. So generally comparing means how it will be, there will be three possible cases. So first one is either it will be greater than or less than or equal to. So these are the three possible cases in this. So in magnitude comparator, for example, if A is equal to A3, A2, A0, these are the number of bits like 1, 1, 0, 0. B means 0, 1, 0, 1. Okay. Now we'll compare, see here. Now we'll compare A and B. So there will be three possible cases. If either A will be greater than B, A is less than B, or both will be equal. So these are the three possible cases we have. Now if we have a 4-bit numbers, okay, 4-bit numbers, will this first here the circuit will be like this A3, B3. Okay. So generally we will get the output as AB plus A bar, B bar. So see here, now A3, B3. Okay. So here we are getting the last bit, and for example if consider this as 1 and this as 0. Okay. So now 1 and 0 means we get 0 here, 0 and 0, 0. Okay. So obviously we will get x3 as 0. So x3 as 0, last bit. So we will get each and every bit here. Now for example this as 1, this as 0 and this as 1. So each and every bit here, and those will be given to OR gate. Okay. These all will be given to OR gate. So this at OR gate, if we get A is less than B, so the first A bits value means A0, A1, A2, A3 are less than. If this OR gate will get 1, this will be A is less than greater than B. If both are equal, here in the sense here it will be measured when A equal to B. So this is 4-bit magnitude comparator. First let me explain about 2-bit comparator. Okay. So I have explained about 4-bit comparator, right? Now we will write 2-bit comparator. A0, A1. Okay. So 0, 0, 0, 1, 1, 0, 1, 1. So A greater than A0 greater than A1. Okay. Take inputs as A and B. Inputs as A, B. A greater than B. A less than B. A equal to B. Okay. So this is very important, 2-bit comparator. Okay. They have asked many times. Now A greater than B means obviously we will get this, right? This will be high and this will be low. Okay. When A less than B means this is A less than B means this is less. Okay. So this will be high and this will be low. And next A equal to B means this is high and this is a high. So this will be the 2-bit comparator. Now we will draw the circuit for this. So A greater than B means when it is greater than B, A bar B means that is A greater than B. So means we have to write here AND gate. See, I will draw AND gate here. A bar, take A bar B. Here A is what? A is greater than B. Okay. In next case, when A is less than B means A bar B. A bar B means greater than B. Okay. So here less than B, whereas A and B bar means A, B bar means we will get A greater than B. When both are equal means A bar B bar plus AB means both are equal. Okay. So this is nothing but XNOR gate. Okay. So this is a 2-bit comparator. Okay. We have discussed 4-bit comparator and this is 2-bit comparator. This is about magnitude comparator. Now I am going to tell about the decoder. So decoder is nothing but if we have n inputs, we will get 2 power n outputs. Okay. So it is a combinational circuit which is designed for decoding purpose, and generally it is used convert BCD to 7-segment decoder. So this is an application for decoder. So generally we have, if we have 3 inputs, we will get 8 outputs, means 3 is to 2 power 3, 3 is to 8. Okay. See here now. 3 to 8 line decoder is nothing but, so first let me tell about the truth table. So we have 3 inputs, right? X, Y, Z are the inputs and outputs are 8 outputs. So when 0, 0, 0 case, this will be high, D0 will be high, 0, 0, D1 will be high, okay. Next 0, 1 case means 0, 1, 2, 3, 4, 5, 6, 7. In this case D0 is high, in one case D1 is high, in two case D2 is high, this one D3 is high, this one D4 is high, this one is high, this one and D7, okay. So these are the cases where 3 to 8 light decoder, the truth table for 3 to 8 light decoder. Now we will draw the circuit, okay. See here, generally first D0, the equation will be x for D0 equal to x bar, y bar, z bar, because 0, 0, 0. Next D1 is equal to x bar, y bar, z. Next D2 is equal to x bar, y, z bar, okay. So D3 is equal to x bar, y, z. So D4 is equal to x bar, x, y bar, z bar, okay. D4 is equal to x, y bar, z bar. Then D5 is equal to, similarly from this I am writing x, y bar, z, okay. So likewise we need AND gates because these are the product terms. So for D0 I have used one AND gate, see here, D2, D1, D2, D3, D4, D5, D6. So likewise I have drawn the 3:8 line decoder, which is very important. So next one is 2 to 4 decoder, okay. 2 to 4 means if we have 2 inputs we get 4 outputs, 2 power 2, okay. So see here, A and B are the 2 inputs, so we will get 4 combinations. See what is E means, nothing but enable button, it is like a reset button. So whatever be the values in the circuit, after pressing enable means whenever we we reset the enable, the circuit will be free, okay. So now output is for A 0, 0, 0, the D0 will be off and remaining are on, okay. Similarly, see 0 means off, 1 means on, 0 means low, 1 means high, okay. Next, see from this truth table I have drawn this, okay. D0 is equal to, see D0 is equal to A bar, B bar from this. Next D1 is equal to A bar, B, okay. Next similarly A, D bar, A, B, okay. So this is the values for D0, D1, D2, D3. So this is using NAND gate construction, that's why the values has been slightly changed, okay. This is 2 to 4 line decoder. We have learned about decoder 3 to 8 and 2 to 4. So they may ask you question like design 4:16 decoder, means if we have 4 inputs we get 2 power 4 outputs, means 4:16. So that is also the same way. First write the truth table for 4 inputs means A, B, C, D. Consider A, B, C as the inputs and outputs are 16 outputs, means D0, D1 till D15, okay. Same process but it takes a long method, okay. Generally they may ask also design 4:16 decoder using 3:8 decoders. So we will get we have 2 3:8 decoders and 1 OR gate, so that we can design 4:16 this decoder, okay. This is very important question in the exam point of view. Next one is De-Multiplexer. See, De-Multiplexer and decoder has a slight relation between them. See, a decoder with an enable input is referred as De-Multiplexer, okay. Okay, we have some enable input, means De-Multiplexer means we have 1 input and we will get the 4 outputs. See here, 3 to 8 decoder. 3 to 8 decoder with enable implement to 4:16. I have said already just now. Design 4:16 decoder using 2 3:8 decoders. So I have used 3 3:8 decoders. I have used 1 enable button. Okay. So 1 enable button means 1 is E and 1 is E bar. Okay. So this from here we get from D0 to D7 values and here we get D8 to D15. Okay. We have discussed about 3 to 8 line decoder, right? Similarly 4 to 16 we use 2 3 to 8 line decoders. Okay. This is very important. So this is about decoder. So next one is encoders. So encoder is nothing but just exact opposite of decoder. So in decoder we have 2 inputs or n inputs, 2 power n outputs, right? Similarly, in the encoder we have 2 power n inputs and n outputs. So here there will be inverse, it is an inverse operation for decoder. Okay, now see here they have given one example, octal to binary encoder. Okay, this is important. First, octal to binary, this is an octal number. Okay, octal means 8 inputs and binary, it is converted into binary encoder. So it means 8:3. Okay, so now see here, just opposite of 3:8 decoder. When D naught is high, the value is 0, 0, 0. So when D1 is high, values are 0, 0, 1. So when D7 is high, the values are 1, 1, 1. So X, Y, Z. Okay, just opposite of inverse operation of decoder. So this is octal to binary encoder table. Okay, next in encoder we have one more topic as priority encoder. Okay, so the encoding process can be done on the basis of priority. Okay, so that will be discussed in next class. Thank you.